Okay, hello. We are going to cover the material for the lecture right now and continue covering the material for the lecture. What we're going to do today is going to be first, we're going to work on capacitors in series and parallel. We already saw resistors in series and parallel. Okay. So now let's see how it works for capacitors in series and parallel. What is going to be the relation, the equivalent capacitance when you connect capacitors in series and we connect capacitors in parallel. So here is the result that we got from the lab. Let me show you here. Here you go. I showed to you that in the lab, that when you have circuits, elements of a given circuit that are connected in series, the voltage across each element, they sum to end up being equal to a voltage V whenever they are in series. Here I put only two elements, V1 plus V2, but you can have V1 plus V2 plus V3 plus V4 plus Vn, okay? And if the circuit, if the branch of the circuit is just in series, the current is going to be the same through each element. Through each element. In parallel is all the way around. What was equal for elements in series? Okay, here you go. In the case, the current becomes equal what was the sum. Remember that? And I'm going to put that the same color here, so you can make a. And what was the sum in one becomes the sum of the other, right? The voltage was summing up, and for elements in series, then if you have elements in parallel, it's going to be the current that's going to sum up. This, you know, the above rule applies to any element, whether it is a resistor or a capacitor. Okay, as consequence, you know, there's an important consequence for this situation that you see right in here. Okay, there you go. Let me highlight here, bold face for you. Okay, what you see here, you go, for this one combined with the Ohm's law, okay, leads to the following result for the equivalent circuit, for the equivalent resistance of N resistors. Okay, here you go. The above table combined with Ohm's law. What is that Ohm's law? V equal to Ri. Result in the following equivalent resistance. Go. For N resistors in series, we get something like that. For N resistors in parallel, we get something like that. So is those two results is a combination of what you see here in this table plus Ohm's law. We can prove that. Possible to prove it. I'm not going to do that. I think it's easier to memorize. It's rather easy. Don't forget that's the inverse of the equivalent resistance. That's what we got in the lab. That's what I showed to you in the lab. For capacitors, you know, for resistors, here you go. I'm going to write that down here. For resistors, the above law for resistors, comma, the above law must be combined. The above table, not law, but must be combined with Ohm's law, resulting in the following relation, the following relations for equivalent resistance. Now, what happens to what happens to capacitors? Okay, capacitors is an interesting relation. Here you go. Is exactly the opposite. For capacitors, the above table must be combined not with Ohm's law, but with the definition of capacitance, which, by the way, is what you have to memorize that, Q divided by V. Okay. Compare, and I'm going to here write that in terms of V. Okay. Q divided by V ends up, being V equal to Q divided by C, right? That's how the electric potential relates with the charge and the capacitance, resulting in the following relations for the equivalent, not resistance, but equivalent capacitance. Equivalence capacitance in a circuit with any n capacitors in series, okay, it's going to be something like that, folks. There's a reason. It's going to be exactly the opposite for what we do for resistors. Okay, so here you go. Compare that, right? And there is a reason. There's a very simple explanation why something like that happens. I'm gonna leave the equation for resistors in there, so you can compare them side by side. Here you go. So if for resistors in series, you end up summing up the resistances, for capacitors in series, you end up summing up the inverse of the capacitance. Okay, side by side. And the equivalent capacitance of a circuit with n capacitors in parallel is this relation right in here, replacing the resistance with the capacitance. Just a matter of substituting the R with the C. Oops. Here you go. And I'm going to leave the relation for resistors in parallel. So it's the opposite. Why is this the opposite? Why those relations? Why the relation? The relations, right? For capacitors in series and parallel is the opposite with respect to the relations. What are the relations for equivalent capacitance? For the equivalent capacitance, in series and parallel are the opposites with respect to the relations for resistances. Okay, so the reason, here you go, lies in the relation for Ohm's law and the definition of capacitance. I already wrote that down, the Ohm's law, how it looks like, right? I'm going to write that down again for you. Here you go. Ohm's law. In Ohm's law, the resistance is directly proportional to the voltage. Remember that? Here you go. V equal to RI. Okay, here you go. In the case of the capacitance, the voltage is not going to be directly proportional to the capacitance. It's going to be inversely proportional to the capacitance, not with a Q here instead of an I. Remember, I is delta Q over delta T, right? So in a way, the relation between charges here in this first in Ohm's law is directly proportional to V, just like we have here for the capacitance. But the way we define capacitance, the capacitance is inversely proportional to the V. So mathematically, that's why we end up having this inversion here. Okay, that's why we end, because Ohm's law, in Ohm's law, the voltage is directly proportional to the resistance, and for the definition of capacitance, the capacitance is inversely proportional to the voltage. That's why there is this inversion here. I'm not going to prove that, but that's the reason that we have this inversion. Okay, if you were to define something else that's not a capacitance, but would be called something else, inverse of the capacitance, then we would have something just like that, just for like that for the resistance. Okay, so that's where the crux of the matter lies. Okay, the reason is that the relationship between resistance and voltage is a direct proportionality, whereas the reason is the following. Here you go. 1A, the relationship between resistance and voltage is a direct proportionality, whereas B, the relationship between capacitance and voltage, is a inverse proportionality. That's the reason. That's why you get that inversion there in terms of equivalent capacitance and equivalent resistance. Okay, so let me show you here a circuit with capacitors in parallel. If we have two capacitors, this can be extended for n capacitors as well. Capacitors C1 and C2, here you go. We can connect them in series. Okay, when you connect them in series to a battery, the right plate becomes positively charged, the left plate becomes negatively charged, because those negative charges flow this way, positive charges flow this way. And once the way it goes like that, here you go. I have to, first we gotta start with two capacitors here, right? They're initially discharged. Those two capacitors, they're not supposed to be charged. Okay? They're not supposed, because they're not connected to a battery yet. Okay. So if you're gonna play the movie, when we connect those two capacitors to a battery, what happens? What happens is the following. First, you can think like that. You go, first, the left plate becomes positively charged, and the right plate becomes negatively charged. That's what happens. First step, because we have those positive charges flowing to the positive here, negative flowing to the other side of this second capacitor. Okay. And then what happens next? This positive charge attracts the negative charge to this plate of the capacitor. Remember, those two plates are very close to one another, and those negative charges attract the positive charges to this plate of the capacitor. Either attract the positive or repel the negative. Either way works, and you end up like that. That's how it works. Okay. So at this point in time, we have a charge Q1 being set up in the plate to the left. And here we have a charge Q2 being set up in the plate of the right one. Okay. And in the next one, it happens that because those two capacitors are in series, the charges end up being equal to one another. Here are the induced charges, okay? And here are the other induced charges. In series, you have this situation in which the electric charges end up being the same in both capacitors in series. And now what happens? You know, the equivalent capacitance in this case is going to be given by the inverse of C1. The inverse of the equivalent capacitance is going to be given by the inverse of C1 plus the inverse of C2. And then you solve for equivalent capacitance. Okay? That's the situation here. So now we can go back to our, there's the lab notes, to our other notes. Okay. Now remember, we got the same current for resistors. We're going to get the same charge for capacitors, and the capacitors are in series. I'm going to put a second one here, current. Here you go. Current for, here you go, resistors. Resistors. For capacitors, you know, we're going to have Q1 equal to Q2. Q1 equal to Q2 equal to Q. Like that. Okay. But don't forget, the current is directly proportional to the Q, right? To the charge. Current is delta Q over delta T. So in a way, not the current, in a way, we can say that this one applies to the capacitor, or this one applies to, this column here applies to the resistor. Okay, charge. Capacitors. Capacitors. What happens when we put them in? Okay, let's see what happens when we put them in parallel. The voltage doesn't change. Just like in resistors. Here you go. The voltage through this capacitor plus the voltage through the second capacitor is going to be equal to V, to have conservation of energy. Okay, V1 plus V2 is going to be equal to V. Okay, that's the equivalent capacitance there. That was capacitors in series. Then we're going to do capacitors in parallel. What happens to capacitors in parallel? Okay, here you go. You connect them in parallel. They're still discharged. The capacitance are the same. When we connect them in with a battery, what's going to happen? The positive charges are going to flow to the plates of the capacitors in the right side, in the left side, and the negative charges are going to flow to the plates of the capacitors in the left side. Okay, here you go. The voltage is going to be the same because they are connected to the same point of the battery. We have the the energy between those two plates is going to end up be equal to the energy between those two plates and those two plates. Okay. But the electric charges are going to be different. The electric charges are going to be different, just like the electric current may be different for resistors in parallel. Going back to our other, but the charges are going to sum up, by the way. They're going to sum up to a value that's going to be Q. That's going to be the charge in the equivalent capacitor. Okay, Q1 plus Q2 is going to be equal to Q. And here you go. Let me show you the next one. Here you go, equivalent. Yeah, the equivalent is Q1 plus Q2. Okay. We have an equivalent charge here. Combine those two capacitors into a single one. And the equivalent charge is going to be Q1 plus Q2, just like you get the same relation for the current with an equivalent resistor. Okay. So that's what we teach. How to connect capacitors in series and parallel, how to connect resistors in series and parallel. Most resistors can be interpreted as a connection of elements in series or parallel. I'm going to write that down here for you. Lecture notes. Most circuits. Go. Most circuit elements can be connected either in series or parallel, but not always. There will be instances in which circuits, in which elements are connected in a way that's neither in series nor in parallel. Okay. Here you go. For these circuits, for you to solve, in order to solve, for these circuits, here you go, you identify the connections in parallel or series. So for the current and voltage. However, here you go. There will be instances in which elements are connected in a way that's neither in series nor in parallel. And you must train yourself to identify those connections in series, to identify those connections in parallel. Let's take a look here at some. Series and parallel. Here you go. This one is obvious, right? That's the simple circuit in series that you're going to see for resistors. R1 plus R2. Batteries in our flash lamp are usually connected in series. When we connect a battery in series, we increase the voltage. Okay. Capacitors in series. Here you go. Here, an example of capacitors in series. A battery, a power supply, and two capacitors in series. Here's the relation that I already did that for you. Resistors in parallel, okay. And then I'm gonna have, here you go, you can have 3 resistors in parallel. And you're gonna reduce that to equivalent resistance. And you have 2 resistors in parallel again. Okay. We can go through those examples. See, here we have a circuit that's more complicated. Here we have a circuit in which this resistor is in parallel with the power supply, and those two resistors are connected in series with each other. Okay, because they're connected in series with each other, the equivalent resistance here in this branch is going to be 6 ohms. And then the 6 ohm resistance is going to be in parallel with the 9 ohm resistor. Okay, and then he goes through the step by step with you. Oops. You solve for the equivalent resistance. And then if you know the potential difference is 0.6, okay? The battery provides a 0.6 volts of energy. There you go. And now we have something else that's a little bit more complicated. It's not obvious, but it's just a matter of figuring out, rearrange what you see right in here to make it look more familiar to you. Let's see if the book did. Here you go. Okay. This point here has no resistor along this line. So it is as though this point here is connected to this point right in here. It's the same thing for this point right in there. Okay. So those three resistors are supposed to be connected in parallel. Okay. Capacitors in parallel. Here you go. That's what we're covering here. 3 capacitors in parallel. Charges. Charges are not the same. The reason because charges are not the same, because V is the same across those two capacitors. If the capacitance is different, the charge must be the same for the charges must be different for the voltage to be the same. Okay, so that's what we have for this part here, series and parallel circuits. Let me show you what I have here. Let's see if we have something else here in my notes. Capacitors in series. Yeah, just a repetition of what you saw before, right? Go, connecting capacitors. Okay, we did that. So in the next step would be Kirchhoff loop law. In the book, they cover Kirchhoff loop law before they cover resistors and capacitors in series and parallel, okay? Most books don't do that. Most books, they first cover resistors in series and parallel, resistors and capacitors in series and parallel, and then they cover Kirchhoff loop law. Kirchhoff loop law is more generic. Okay, here you go. Here are examples of how to connect resistors in series, right? 3 resistors in series. First, you connect one with 2 in series to use the equivalent resistance, okay? And then you connect the other with the third one. And then you can have combinations, not just combinations of circuits, just plain circuits in series and elements in series and elements in parallel. You can also have a mixture of both. Here you go. You can have a mixture of both. Circuits in series, two elements in series are connected to one element in parallel. Okay? You need to practice those problems that at home. You identify that those two are in series. So you can relabel them as R12. Now that you relabel them as R12, you can identify that this equivalent resistance R12 is in parallel with the resistance R3. Okay? Series, parallel, and what the resulting element, the resulting equivalent element, I call resistor 1, 2, 3. Okay. Oh, okay. And now when we get to this point, like I said, not every element can be connected in series and parallel. You can solve most of the circuits problem by recognizing that elements are either in series or in parallel. But then we have those oddballs out there in which they're not connected either in series, not in parallel. Okay. That's the case of the bridge circuits. If I were to remove this resistor from here, then I would say that those two are in series and those two are in series because they're connected to the same potential difference. But because we added this oddball right in here, there is no way I can interpret those guys being series or in parallel. It's a mixture, it's a combination. For this type of circuit, we use, in order to solve this type of problem, we use Kirchhoff loop law, which is here's another example in which we cannot solve a problem in terms of elements in series and parallel. In this case, we have two batteries that end up being series working against each other. Again, we use the technique of Kirchhoff's loop law. And I'm going to do the step by step with you, okay? Here, what we do. That's the simplest problem that I'm gonna get out there that will require you to use Kirchhoff loop law. What do? In this case, we set up a loop. We give it a name, number 1. Okay? Give it a name, number 1. Loop number 1. So there are loops, and sometimes there will also be nodes. Okay, let me. This one here. Okay. So all I have to do is to erase that, make it look better. Right? Because now I don't need this one anymore. Okay, we start with this circuit. What do we want to do? We want to find out the current through the circuit. We know V1, we know V2, we know R1, and we know R2. Let me give an example so you will understand how you apply Kirchhoff's loop law to this type of problem, right? So let me write that down in my notes. Yeah. There will be instances in which elements are connected in a way that's neither in series nor in parallel. Also, there will be problems in which you will have two batteries as well. Batteries as well. In these cases, we use a different technique called the Kirchhoff rules. You go. Series and parallel, Kirchhoff rules. The Kirchhoff to H's and to F's. The best way to understand Kirchhoff rules is by looking at an example. Okay? So what do we do? First, identify loops and nodes of a circuit. Okay. Loops is what you saw in there, and nodes is that point where two wires cross with one another. In this example that you see right here, there's no nodes in this example. Okay. Then what do? You set up. First, you identify the loops and nodes, right? Then choose direction for the loop, for each loop. Clockwise, you can choose it either way you want, either clockwise, or counterclockwise. Okay. Either clockwise, W, or counterclockwise. Clockwise, CCW. What do we do next? Set the direction of the current. You can set the direction of the current any direction you want. In this case here, I set the direction of my current in the clockwise direction, in the same direction of my loop. You do not know the loop, you do not know the current, you do not even know the direction of the current, but you can set up in which direction you want. Okay. We go. You know, set the direction of the unknown current. Either way, you know, either way you want. And then what we do next? We count the drop or rise in voltage. You count the drop or rise in voltage. Let's see here. Then you account, right, for the drop or rise in voltage along the elements of the circuit. So the way you do it, here you go. I'm gonna take this one out because first I set up the direction of the current. I don't need that yet. I want to make it go. That's the last step that you do, the points in the circuit, okay? A, B, C, D points. Here you go. Okay, so let's do that step by step. Here you go, circuit. There are two batteries here in the circuit. And you do not know if those resistors are in series or parallel, because you have added a second battery, a second power source, a second electromotive force. Okay, so what do you do for Kirchhoff loop law? You know, you first set the direction of the loop, identify the loops, right? And identify the nodes. There are no nodes in there, there's just one loop. Next, you set the direction of the loop. I set up this direction. You could have set up the other direction as well. No problem. Set up the direction of the current. Either way works, like I said. And then start identifying the points in the circuit so you can account for the drop or rise of voltage. Drop or rise in voltage. Okay? Go. You want. Account for the, let's see, identify points in the circuit next to each element. Points next to each circuit element. Let's put identify points next to each circuit element. That's the next step. Okay, you go, and that's what I did here. Next to this element here, this one is also next to this element. Okay, this point here is being shared by this element here in the circuit, this side of the element in the circuit, and this side of the element in the circuit. This point too is sharing, is being shared between both elements, and so on. Count for the rise or drop in voltage as you walk along the circuit, as you not walk but move along the circuit in the direction, along the direction, as you move along the circuit in the direction of the loop. Okay, so from A to B, let's do that together. Here you go. from points A to B, in my example, what do we have? Let's take a look. We have, when we walk from A to B, we have a rise in electric potential from lower potential to higher potential. The negative is at a lower potential than the positive. So what we do? We write down the following equation from points. You set up at positive V1. Okay, that's what you do. That's the first. We have plus V1. We have plus V1. Lower. From B to, what about from B to C? Let's see what happens from B to C. From B to C, we are crossing a resistor. From B to C, we are going to cross this resistor, and we are going the same direction of the current. Because we are moving the same direction of the current, we are going to have a drop in potential, in electric potential. That's going to be given by Ohm's law. It's going to be R1I with a negative sign in there. Here we go. So okay, it's going to be minus R1 I. Oops. R1 I. Like that. See the negative sign here? So now we're going to move from C to D, which is, C to D. In my example, let's take a look. Now we're moving from the second battery, from a electric potential that's a higher point to electric potential that's a lower point. So because of that, we're having a drop in electric potential here across this element, this third element in the circuit. So what we have, we write it down, minus V2. And all of that is going to result in an equation. V2, not V1, but V2. Until we go a complete circle. Until we move a complete, we go from D to what? From D back to A. Back to the original point. In my example, we're going to have what? We're going to have a resistor 2 times I. And because we're moving along the direction of the current, it's going to be a negative value as well. Here we go. R2 times I. Here you go. The resulting, what we have, those are all the drops in potential. So when we start here and come back to the initial point, we have a net potential of 0. So if you sum all those values, here you go, I'm going to do that for you. The sum of all those 4 values here should be equal to 0. Insert. An equation. Let's copy this one here. Make it simpler. Here we go. What we're going to have here, we're going to have plus V1. We do all of that, whether it's for a resistor or for a capacitor, okay? This type of procedure works both for a resistor and a capacitor. I1, not I1, but I. There is just one branch, so there wouldn't be any I1 there. Here you go. We're gonna get minus V2. Here you go. And gonna have minus R2I. Minus R2I. And what's gonna go in the right side is gonna be 0 because we have gone full circle. Like I said, this is the easiest type of circuit of problem that I'm gonna see out there. Solving for I, we get, here you go, those here is gonna be negative, right? This is gonna be positive. I'm gonna multiply both sides by -1. So I can change the signs of the currents, of the terms that contain the currents. We can pass V1 and V2 to the other side now. Here we go. And we invert their signs. There you go. V1 minus V2. We get this difference here, V1 minus V2. Why is that? Because this battery here is working, is pumping charges in one direction. This one is pumping charges in the other direction. So one subtracts from the other. Okay. If this battery was inverted here, then we would have that V1 plus V2 instead. Keep that in mind. In the next step, we are going to put I in evidence, and we can solve our problem. Like I said, that's the easiest type of problem that you're gonna see out there when it comes to loops, Kirchhoff loop law. R1 plus R2 goes to downstairs, and that's what you get for the current in your circuit. If V2 ends up equal to V1, then you have no current flowing. If V1, here you go. If V1 equal to V2, then no current flows along the circuit. Okay. If V1 greater than V2, then current flows, there you go, magnitude, right? Yeah, okay, no, that's okay. Yeah, it's the magnitude. This V1 and V2 are both greater than 0. Then current flows in the clockwise direction. Okay. Now, if you have the other case, the last case, if V1 is less than V2, then the current is going to be negative. The current, then the current is positive. Here in this case, is positive and flows in the clockwise direction. If V1 less than V2, then the current is negative and it flows in the counterclockwise direction. Okay. time that you get a negative current value, it means that you chose the wrong direction, wrong between quotes. It's not necessarily wrong, provided you interpret it properly, okay? So you have those three situations. Here you go. Next one. Here you go. We have a circuit that's more complicated here now. We have a circuit now that has two loops and two nodes. Nodes where you have an intersection here. Okay. So let's start it here. Here you go. Let's say we do not know another example. Okay, Kirchhoff loop law. An example that's a little bit more complicated. Let me erase those current values here. You can choose what, you can choose whatever value, whatever direction you want. Here you go. So first step, let's see here. Yeah, the first step, let's get the steps here that I spelled out, okay? You know, those steps doesn't have to be necessarily in this order. But let's here you go. I'm gonna do the following. I'm gonna get this one here. Identify the loops in the circuit. Okay, there are three loops, not two, but three loops. We have the two inner loops, and you have the outer loop. Okay, see this loop number one, loop number two, and loop number three. I'm making all of them in the clockwise direction. Again, it doesn't matter if you put clockwise or counterclockwise. Okay, we identify the nodes. There are two nodes here. Let's go for the next one. I'm gonna even identify the loops in the loops of the circuit. Two. Identify the loops of the circuit. We go of the circuit. Identify the nodes of the circuit. Of the circuit. Okay. So that's going to be the next step. Go. And I'm going to mark the nodes. One node here. I'm going to make it this node black. Okay. I'll call it node A and B, let's say. Identify them and name them. Identify and name them. It's going to be nodes A and B. I'm using letters for the nodes, numbers for the loops. A and B. That's what a node is, an intersection where current may either split or combine. What else? Here we go. Identify the nodes of the circuit. Identify and label, right? Let's put this way. Identify and label the loops of the circuit. Identify and label the loops of the circuit. Okay, in this case here. Oh, here we go. One more step that I should put here, you know? Choose a direction for the loop, either clockwise or counterclockwise. Here you go. Let me that. Identify and label the nodes of the circuit. In the next step, we're going to set up the direction of the current. Go. Ooh. And that I have chosen to set up a direction for the current. You know, we must have one current flowing in this direction. We must have another current flowing in this direction and another current flowing in this direction. Can be either I1 can either be from the left to the right or from the right to the left. I have chosen from the left to the right. Here too can be even upwards, downwards, or can be upwards. Here too can be even downwards or upwards. It's up to you how you set it up. So what I gotta do here is let me see if I need to do that. Yeah, I don't need to do that. Okay. So let's go get it. I don't need this next slide. I'm gonna eliminate this slide. Go. A. Node A. I don't need that anymore. Let's go through that so you can revise what we did, right? Here's the circuit. Find the current. You know R1, R2, R3. You know V1, V2. Find the current. Identify the nodes, the loops, and set their direction. Identify the loops, label them, and set their direction. Okay. Identify the nodes and label them. And now set the direction of the current. Each branch must have a current. See, we have only the current that's flowing through this whole branch is the same because you have those two elements in series. The current that's flowing through this whole branch is the same. So if you have I2 here, you must have I2 here as well, going upwards, I2 going upwards. See, similarly here, you know, you have I3 over along only this branch. Okay, so here you go. Set the direction of the non-current. Either way you want the non-currents. Either way you want. Identify points next to each circuit element. You know, I label this one as A. I label this one as B. Let's say this one is C, D. Okay, we don't need to put, yeah, C. Here can be C, but here there is no need to put another point because there is no element here. Okay. So the only one that you have to label, we have to label another one here between those two elements, right? So here you go. We have this one. Here you go. Let's say I'm going, oh. Put it here. That's going to be C. Point C. This point B, you know, is next to this other plate of the power supply. And I have to put another point here between this resistor 1 and V and the power supply V1. Those are not necessarily nodes, okay? They're just generic points along the circuit. Maybe I should give them different colors, right? So you do not mix them up. Oh. D. Let's give them different colors. Ooh. Give them different colors. Okay, you know, gotta make the, oh no, not that one. Okay. I'm just giving them different colors so you know that they're different type of points, more important type of points. Because they're the nodes. I'm going to give the letters a different color as well. But you are still going to use them in the solution of this problem. So we have 3 loops and 2 nodes. Each loop and each node are going to provide us with an equation. Okay, so in the previous problem, we had just one loop and 0 nodes. In this one, we have 3 loops and 2 nodes. A more complicated problem. Each loop, like I said, each loop and each node are going to provide you with an equation to solve your problem. And you're going to end up having a system of equations. Okay, a system of equations to solve, which you will be able to solve. Let's take a look. Loop 1. Loop 1. Example 2, right? Loop 1. I'm not going to go through this point A through B, okay? I'm just going to go straight to get the equation for you. Here you go. Don't forget I2 here, this point is downwards. At this point, it's going to be to the right. At this point here, it's going to be to the upwards. Okay? So let's start from C to B, okay? From C to B, we lose electric potential, V2. From C to B, we're going to have a minus V2. Let's see if we can take advantage of what we did before, right? We're going from higher potential to lower potential. Okay, we're doing loop number 1. Then we are going to enter loop number 1 right in here against the flow of the current I1. I set up my current I1. So I'm moving against the flow of the current. The loop is clockwise, which is also going against the flow of the current. Because I'm going to go against the flow of current, I'm going to gain electric potential across this resistor. Okay? So now what we have plus R1 I1. Don't forget that now we have a current value I1. And whether you gain energy or lose energy across a resistor, it all depends on the direction that you're moving along the resistor. Uphill the current, you gain energy. Downhill the current, you lose energy. That's why I have plus R1 I1. Now we're going to go through this battery from higher potential to lower potential. You're going to lose energy no matter what the direction of the current. You're going to lose electric potential. It's going to be minus V1. Minus V1 right in here. There is one more that I have to worry, right? So let me just give a little bit of space here. One more element. Here you go. I went through V2, I went through R1, I went through V1, and now I'm going to go through R2. I'm moving up, along the direction of the current through this resistor R2. So I'm going to lose potential. Minus I2 R2. Minus R2. Here you go. I2. And then we go full circle. We get equal to 0. We are done with loop number 1. We're done with loop number 1. Okay, what about loop number 2? There's a little secret about this loop law. Okay, and I'm gonna tell you very soon. Just stand by. Let's go through loop number 2, and then we worry about loop number 3 next. Here you go. Let's start with a point D, or let's start at point A. Let's start at point A. Okay, we move from lower potential to higher electric potential. So it's gonna be plus V1. Plus V1, okay? I'm gonna emphasize the fact it is V1 here. Plus, that is positive. From D to B, we are going to lose electric potential because we are flowing along the direction of the current. It's going to be minus R1, I1. Minus R1, I1. Okay, we are going to get down here and flow through resistor 3, and we are moving at the same direction of the current, so we're going to lose current as well. Minus R2, R3, I2. Let's see, minus, let's go back there. R3, I3. We do not have a second power supply there. You go. Go back to initial point equal to 0. Okay, this loop. So we are done with loop 1, we are done with loop 2. Notice that so far we have 2 equations, but we have 3 unknowns, I1, I2, and I3. Okay, let's do the loop 3, and then I'm going to tell you a little secret that I'm going to go. Loop 3, we're going to do, in reality, you don't need loop 3, but we're going to do anyway, just for practice purpose. Okay, loop 3 is clockwise. So we are going to lose electric potential along V2. Okay, so I'm going to copy this one here. Some parts of loop 3 coincides with some parts of loop 1, right? So we pass across V2, moves along R3, you're going to lose electric potential as well along R3. So we must have one element from loop number 2 there. And finally, we have R2 that's flowing along the current. We're going to lose electric potential as well. That's going to come from loop 1. We don't go through. Okay. So only 3 elements for loop number 3. 1, 2, and 3. 3 equations, 3 unknowns. Okay. But we can get 2 more equations. We can get 2 more equations from the nodes. Node A. Here we go. Node A. Let's take a look here. Here at node A, let me get current I3 here on the other side as well. Here you go. Current I3 here on this side is moving uphill, upwards. Okay. Format shape. Let's get it in the right direction. Here you go. That's where I3 is moving. At node A, I1 is moving away as well from A, right? And I2 is moving upwards. So what's happening here? What's happening here is the following. I3 is coming here and splitting into I2 and I1. Okay? Let me get the I2 there as well, so it makes it easier for you to visualize. Again, visualize those things just like the flows of cars, where the cars are the are the electric charges moving in a circuit like that, okay? I2 here must be moving this direction. I1 here must be from the left to the right. So what's happening here? I3 is getting to this point and is splitting into I2 and I1, okay? And then what do we get? We get I3 equal to I2 plus I1. That's what this equation is telling us. Node A, here you go. I3 is equal to I2 plus I1. Go. By the way, you're going to get exactly the same equation for the node A, node B, okay? Remember, I told you you need only 3 equations to solve this problem. Now we have 4. We're going to have 5 equations instead. So what does it tell us? It tells us that we need only, remember, we need only 3 equations. So what does it mean? It means that 2 equations are unnecessary. 2 equations that you're seeing right here are going to be unnecessary. And I'm going to show you which one is going to be. Here you go. Here's the same thing. I1 plus I2 combines into I3. Okay? I3 is moving away from the point. So I1 plus I2 combines into I3. Exactly the same equation that we had before. The only difference, here you go. I1 and I2 are coming to node B, right? And they're combining. So those 2 equations are the same. This one is obvious, right? So you can, note that the equations for nodes A and B are the same. Okay, so we don't need, so we can disregard one of them. Okay, so here you go. I'm going to copy and paste here. I'm going to disregard the equation for node B. And now we have 4 equations for 3 unknowns, I1, I2, I3. So what's happening here? Okay, one of those 3 equations here must be dependent of all of the other 2. Okay? So you have to, now we still, here you go, we still have more equations than we need. Okay? For equations for equations for 3 unknowns. Over a problem. Our problem. We may, what does it mean? It means that one of the loop equations is dependent of the other 2. So to solve our problem, we can disregard one of these loop equations. It doesn't matter which one we disregard. Okay. Preferably, you disregard the most complicated one, the one that has the large number of elements. So it makes it easier for you to solve the problem. Preferably, you disregard the one that has the larger number of elements. Okay. It is, it is more convenient to simplify the solution of the problem. Problem, comma, disregard that equation that has the greatest number of elements, group 1. Okay. So we go, we end up with those 3, and we end up with only with the right number of equations that we need, with the necessary number of equations that we need. Now we have 3 equations for 3 unknowns. Now we have 3 equations for 3 unknowns. And we can start solving this problem. Okay. Okay, so it's just a matter of applying now your mathematical skills. Let's start with solving for I3. Okay. Sometimes it's very, cumbersome to solve that, but you have learned that in algebra. What we're going to do, eliminate I3 from the equation. I'm going to substitute I from this system of equation. I'm going to substitute I3 right in here and right in here. Okay. So first eliminate I3 from the system of equations. Go, copy and paste. I3 is gonna go here. And it's gonna go here. Okay. I don't need that equation anymore. So I can eliminate that. Now we have 2 unknowns, I1, I2 for 2 equations. Okay. So let's see what we can do here to continue solving our problem. Let's eliminate I2. Okay. Now eliminate. Now it doesn't matter which one you eliminate. Okay. Eliminate I2. We eliminate I2 by writing I2 in terms of I1. Okay, so here we go. Here we go. Because we have the same thing here, right? Okay, here we go. I'm going to eliminate the parentheses. We do not need the parentheses. Neither one. Go. R3, okay, we have the same thing here. Hopefully I didn't do any mistake, didn't make any mistake, right? Eliminate I2. I'm doing all of that in a, okay, I can eliminate I2 from this first equation. It's easier to use the first equation to eliminate I2. I'm gonna multiply everything by -1. Negative. Okay, pass what's not I2 to the right side. There you go. Right? There you go. And then we divide by R3. Go R3. Like that. And finally, substitute I2. Now I2 is in terms of I1. we can substitute right in here and solve, substitute I2 into the second above equation and solve for I1. Okay, then feed back I1 into the I2 equation. Okay. And the solution for I1 and I2 for the I3 equation. How do you do? So that basically, I'm not going to finish this problem. Okay, you can do that yourself. I want you to practice. This is just an algebraic type of problem, and you can do that easily. Okay, but the setup, the secret to solve this type of problem is by doing what I did before, right? Doing what I did before. Here you go. Identify the loops and the nodes, set up the equations, recognize that we have more equations than we need, and you disregard one of the equations of the loop and one of the equations of the node. That's the whole secret of the whole thing. Okay, here you go. I have all the nodes A and B here and so on. And then what I did here in the PowerPoint, let's see. Oh, okay, stops here. So we can stop right now. And I see you again some other time. So see you soon.